Hello students, this is Dr. Amrita, Assistant Professor, Department of Physics, Patna Women's College. Today we will discuss about Fourier series and Fourier coefficients. It is a mathematical tool which is used very widely in the field of acoustics, optics, quantum mechanics and so on. It is applicable for only those waveforms which are periodic in nature. We come across a number of physical variables which show periodicity with respect to time or spatial coordinates. Using the help of this series, we can obtain the resultant of a number of sinusoidal oscillations which is known as Fourier synthesis. Also, we can obtain the components of any given complex waveform as sine and cosine functions, which is referred to as Fourier analysis. We must be able to understand first what is meant by harmonic motion. In harmonic motion, the dependent variable oscillates either sinusoidally or cosinusoidally with time. So, suppose we have y equals a sine 2 pi nu t. In this wave, a represents the amplitude, nu is the frequency and 2 pi nu is the term for angular frequency omega. An important quantity is the time period of oscillation, which is defined as t equals 1 upon nu. So, if we are having two harmonic oscillations of same frequency, then their resultant will be a harmonic one with same frequency. Also, when we superpose a minimum of two oscillations of different frequency, then we will not get the resultant as harmonic. These two properties of harmonic oscillations can be proved very easily. Let us consider a third case. If the given oscillations are having different frequencies, but all are multiples of a fundamental frequency, then the superposed wave will be periodic in time with a time period t. The most common periodic functions are trigonometric functions with period 2 pi. In electromagnetic theory, we have electric and magnetic fields as periodic functions of r and t. The wave function psi is also periodic in most of the quantum systems. The theorem put forward by Fourier, which states that two or more simple harmonic vibrations can be combined to form a complex periodic waveform. The frequency of the complex waveform is determined by the greatest common divisor of the given frequencies. Using this theorem, both analysis and synthesis of periodic functions can be done, which we will work out in the applications part. The theorem states that a given complex waveform represented by y, which is a function of omega t, is composed of a number of harmonic functions in omega t. In expression, it is written as y equals a naught plus a1 cos omega t plus a2 cos 2 omega t plus a3 cos 3 omega t plus b1 sin omega t plus b2 sin 2 omega t plus b3 sin 3 omega t and so on. It can be written in form of summation also with one constant term a naught and one cosine and sine series. Here a naught, ar and br are known as Fourier coefficients. In the given expression 1 of Fourier series, omega is known as the fundamental frequency. A naught represents the initial value of the function y independent of time. The sine and cosine terms represents the different harmonics of the waveform, each corresponding to different values of index r. If we are given any waveform, then we can find the components by obtaining the Fourier coefficients by making use of Euler's formula. It also shows that if we have an infinite series, the more number of terms we include, the more accurate waveform we will achieve. Let us understand this using an example. In the given plot, I have plotted first the harmonic wave of frequency omega in the interval 0 to 2 pi. In the same figure, we can see the plot of a by 2 sin 2 omega t, a by 3 sin 3 omega t and a by 4 sin 4 omega t also. In each wave, amplitude is reduced and frequency is increased. One plot of violet color is the sum of all the 4 oscillations and it is a complex one, but of course it is periodic. If we keep on increasing the number of sinusoidal terms, we considered we will obtain a sawtooth wave. The analysis of such a kind of wave we will study afterwards. The plot which I have shown is taken from Mathematica notebook. You can also check it by registering on www.wolframcloud.com and creating your own notebook and analyze further. Let us move to another example. I have plotted a sum of harmonic terms which are not having any specific relation between their amplitudes and frequency. So the resultant is a complex wave, but it is neither a periodic function nor continuous and bound. So there are some conditions which must be satisfied by the function, then only Fourier's theorem can be applied to it. Let us move to the formulae for obtaining Fourier coefficients, because only if we obtain the coefficients we can analyze a complex waveform. It shows that if we have a variable y represented as Fourier series, then the Fourier coefficients are given by a naught equal to 1 upon t integration 0 to capital T y dt, AR equals 2 upon t integration from 0 to capital T y cos r omega t dt, and BR is equal to 2 upon t integration 0 to t y sin r omega t dt. These can be proved very easily using equation 1. We shall discuss further how to calculate Fourier coefficients for different kinds of waveforms. Thank you.